So thank you very much for inviting me to this meeting. I congratulate the organizers for putting together this very nice program. And since Sumilan is my very good friend and colleague, he has agreed to give me a few minutes extra. Okay, so I'm going to talk about something called unnecessary quantum critical points. And the title has the word pencil, and this word pencil is not a noun, it's actually a verb. So I'll try to explain to you what that means. Right? Okay. All right, so it's a good place to start with acknowledgements. So the real contributor to this work is Basudev Mandal. He is a postdoc at IISc and he's a wonderful person to interact with, and he has done most of the work. I'm just giving the talk. So I've been inspired by a talk that Abhishod gave. Abhishod Prakash is at HRI. He gave a talk at IISc, and this whole work sort of started from that talk. I've had lots of discussions with him.
Hello.
And yes?
Hello.
Yes? That's from the other hall?
Hello.
All right.
Hello.
Okay. All right. So I've been generously supported by ANRF over the years, even while it was the erstwhile SERB. Okay. So what I'm going to do is I'm going to discuss a little bit about symmetries and phases and classification of phases. Then I will follow that up with the idea of critical points, and I will discuss what do we mean by necessary and unnecessary critical points. I will introduce the notion of what a pencil means. And then my main story is that what we call as unnecessary quantum critical points are penciled by necessary critical points. And I will present, I will not do this in a mathematical way. Actually, I should turn this off. Sumilan. Okay, good, that's much better. Okay, I'll present evidence based on examples, and then I will have a short discussion of what are the things that we still don't understand and what we are working on. And my conclusion is that the title of my talk will be modified. Okay, so that's going to be my conclusion. Okay, so what is, if you ask me, or ask any reasonable physicist, what are some of the great things that happened in the last 20 years in physics that will last for a long time? This is the classification of phases. So it has been understood based on experiments and a lot of theory that the usual insulating and metallic phases are not the only phases of electrons. There can be many other different phases. And the central notion that goes into the classification of phases of particularly fermionic systems is the notion of intrinsic fermionic symmetries. So if you look at what are the intrinsic symmetries, fermionic systems and other systems as well can have something called time reversal symmetry. This is true for all quantum systems. But when you have fermions, there is an additional operation you can do on fermionic Fock spaces, which is you can transform particles to holes and vice versa. So this gives us a new kind of symmetry called as charge conjugation symmetry. And when the charge conjugation symmetry, this particle hole transformation, is a linear symmetry, then you call it charge conjugation. And when this particle hole transformation is an anti-linear symmetry, you call it sublattice symmetry. So these are the sort of abstract symmetries that a fermionic system can have. And you can have combinations of this. So if you look at the combinations, you will see that fermionic systems will organize themselves into 10 distinct symmetry classes. So these symmetry classes are labeled here. And they turn out to be projective representations of the Klein-4 group, which is formed by these symmetries, or subgroups thereof. Right? So you'll end up getting 10 symmetry classes. And what these, I'll just take one particular example. Take this BD1 for example. So you see that's +1, and 1. That means that this symmetry class has all these symmetries, time reversal, charge conjugation, and sublattice. And t square will go to +1. That means projectively, if I square t, it will just give you identity. Whereas if you compare with, say, C2, the t square will go to -1, which means it's only projectively identity. Right? So this is what happens. Now the way this picture is organized, you see that the topmost layer here, that's called class A, and you see that has no symmetries. None of these intrinsic symmetries are there. Whereas if you look at the second row, you will see that it has exactly one of these symmetries, and the third row has all of those symmetries. So in some sense, this the bottommost layer here is the set of all high symmetry fermionic systems, and progressively you can reduce symmetry and come to class A. So I may use paths like this in my talk. Okay. So in any dimension, any fermionic system, they will fall into one of these symmetric classes. Now when you want to classify free fermionic phases, what you do is you look at these symmetric classes, and this is spatial dimension. I lifted this picture from somewhere on the internet, and you see that in any dimension there will be 5 symmetric classes which have some non-zero entry. Whenever you have a non-zero entry, what it means is that there are distinct gapped phases of fermions. Okay, so that's what it means. And so non-zero entry in the symmetric class in a given dimension indicates the presence of topologically distinct phases. So these are also called as symmetry protected topological phases. And if you look at the space of Hamiltonians, say for example you look at any one of this, say A1 in dimension 0, you will see that you can think of some space of parameters to describe the Hamiltonian. And what happens is that that space is divided up into disconnected chunks. So for example, you cannot go from this side to that side without crossing one of these blue lines. And those blue lines are what I call necessary critical points, because they are separating 2 distinct topological phases. So they are necessary in that sense. Okay. So I just mentioned this is what I just discussed. And let me go on to show you, I just said that these loci are the critical points. So the most elementary example of this is the famous SSH model. So what you do is you take a chain and you have spinless fermions, and there is some staggered hopping. So there is some hopping T1 within the unit cell, and there is a T2 going to the next unit cell. And you will see that if you just study this, which many of you have done in your courses, you will see that there is a quantum phase transition that occurs when T2 by T1 is 1 as you tune T2 over T1. And this point is actually a necessary critical point, in the sense that it separates 2 distinct topological phases. Okay? And this is of course consistent with the classification which I have just drawn a sliver of here. So you see that in this problem will fall in what is called as the BD1 symmetry class, and you will see that Z classified. That means there are infinite distinct topological phases with different topological numbers called winding numbers. And this is an example of going from winding number 0 to winding number 1. So this is what we mean by necessary quantum critical points. So when can we say something is unnecessary, or when should we say something is unnecessary? Okay. So where do we cite the first unnecessary critical point? I'm going to show you an example which I learned from Abhishod. So you take the SSH model, right? And what you do, you change the symmetry class of the SSH model. How do you change the symmetry class of the SSH model? You want to retain time reversal symmetry, but you want to kill the sublattice symmetry. So what you do is you just introduce some ionic potential. So you lift this guy's energy up and push that guy's energy down. Okay, so this will take you out of the BD1 symmetry class, and you will be in asymmetry class. But remember, asymmetry class in A1 symmetry class, it will go to the time reversal symmetry plus 1 symmetry class. That's A1. You will see that that has 0 classification. That means if you take time reversal symmetric Hamiltonians in one spatial dimension, it does not hold distinct topological phases. So any gapped state and any other gapped state can be connected to each other by a path in the space of Hamiltonians without crossing any phase boundary or without closing the gap. But you see, suddenly you see that in the origin of this, or this T2 by T1 equal to 1 and E, this point is a point where the gap closes. So it looks like this point is unnecessary from the perspective of the class A1, right? But you may say, okay, that's not so interesting, because there is already this BD1 line sitting here, because if I put E equal to 0, that's the BD1 manifold. So you will just say that's just the BD1 critical point. But what Abhishod, etc. showed in their paper is that if you look at this BD1, this is the BD1 line, and if you go along E, you are in class A1 now, and you add any other parameter, like it could be interaction, it could be any different parameter you can add, and take it again, keep the whole thing in A1, you will see that this critical point will continue on. So for example, if I'm at a finite lambda and you think of a plane here, that will have a point in the plane which is critical. But that shouldn't be there, because A1 has no non-trivial classification. So you see, and the important thing is that I can go around this critical point without closing the gap. So there is only one phase there, but in between, suddenly there is a critical point. So this is what we mean by unnecessary critical points. Okay. Okay. So unnecessary critical points were introduced in this paper to the, at least to the best of my knowledge, this term was introduced by Bai and Senthil in this very interesting paper. I will not go into too much into the details of that. I'll stick to free fermions. That paper is much more, discusses more interesting models, right? And any two gap points in this, so you're thinking of a system which is in a symmetry class, which hosts no, which has just boring, it's just a single phase. And what you can do is, in that space, you find there are some submanifolds which are critical. And those submanifolds will be in such a way that their codimension has to be greater than or equal to 2, if those submanifolds don't have any boundaries, right? If it is greater than or equal to 2, then you see, even if this critical surface is there, unnecessary critical surface, you can go around the critical surface. So imagine that I have a three-dimensional thing where there is a one line which is unnecessary critical. Then you see I can always go around that. That's what I mean by codimension greater than or equal to 2. Okay? So Abhishek's example is a very nice illustration of that. Okay. So what is the scene? The scene is that I have Hamiltonian spaces such as A1, which do not host any distinct phases of matter, yet they host submanifolds which host distinct phases. If you stay on the BD1 submanifold, then there are distinct phases. Okay? So the question is, how are these unnecessary critical manifolds related to the critical manifolds on the submanifold of higher symmetry? That's the question. So what we're going to do is, we're going to start with this system which hosts SPT phases, and we are going to sort of break symmetry, if you like. We are going to add terms to the Hamiltonian, and we're going to study how this critical surface evolves. Okay, that's the strategy. And my answer to the question that I'm asking here is the title of my talk, which is that unnecessary critical surface will pencil the critical points. So natural question, what do you mean by pencil? Right? Okay. So mathematics has a very, very fancy definition of pencil, which I will of course avoid. So a pencil is a family of manifolds that touch a common manifold, right? So the common manifold is called as the base locus. Okay? It's also called the axis. So now you can see how the word pencil is used to this, right? It's used to describe this. So imagine you have take a pencil that you have. It has a conical thing. So if you draw lines from the tip of the cone down, there is a family of lines. Those family of lines will touch the apex of the cone. And we say that the pencil of those lines is the tip of the cone, right? And the tip of the cone is actually the base manifold or the base locus. Right? So this is an example. So this is the pencil example that is shown here. And the next example that is shown here is this one is a set of planes, and you can have more fancy pencils like this. And some of the examples I will show you indeed have things like that. Okay. So what is the final statement? The final statement is that the necessary critical surface is the base locus of the pencil of unnecessary critical points. That's the statement. Okay. All right. So I'm going to start by 0 dimensions. Okay, you may take issue with this because in a finite set of orbitals, you shouldn't think of as quantum phase transitional because it's a finite system. But this will illustrate the idea, and then I'll of course show you things in higher dimensions. So what I'm going to do is I'm going to start with class BD1, which has symmetry signature ++1, that is 1, 1, 1, and A3 has only sublattice symmetry. So if I take BD1 and break time reversal symmetry or something, then I will immediately go into A3. Keeping sublattice. Okay. All right. So this is what I start with. So if I start with BD1 with just what is the simplest model in 0 dimension I can start with 2 orbitals, right? And if you do that, you will see that the BD1 Hamiltonian looks like this. There is one phase here and another phase here, and that is separated when h is equal to 0. So it's kind of boring. And if you make it A3, I just add complex terms, and now you see you can go from any point in A3 to any other point in A3 by this path, and you avoid 0, and so there is only a single phase in A3, but there are 2 phases in BD1, and so its Z2 classification is same. Okay? So this is illustrative, but it doesn't show you this pencil idea. So what I'm going to do is I'm going to take exactly the same problem, but increase the number of orbitals. Okay? So I'm going to increase it to 4, and when you go to 4 orbitals, you want to parameterize the space of Hamiltonians. So you invent notation like this to write down tensor product of two Pauli matrices, and these are all 4 by 4 matrices. So if you now use the standard definitions of what are the symmetry transformation matrices for T, C, and S, you will see that the BD1 Hamiltonian is described by this, this object here. Okay? It's a 4 by 4 matrix written in this language. So if you look at what is the space of BD1, you will see the space of BD1 is just the 4-dimensional real space, right? Because you can put any real values for this, right? But this includes the origin, which is kind of a boring point, so you remove that. So what you will get is, if you remove the origin, you can easily see that this is S3 cross R. So technically speaking, if you take the origin out and take R4, and S3 will be the deformation retract. That is, you can just squish all the radial lines to the unit sphere in 4 dimensions, and that will be S3. So morally, the manifold of BD1 is S3, right? This is just a scale factor. Okay, so there is a way to parameterize S3 using this, or the BD1 parameters using this set of angles. This all requires Basdev-Mandal's genius to work out here. Okay, and what you can show is, I'm not going to show any calculations, is that whenever delta 1 is not equal to delta 2, so delta 1 and delta 2 are the magnitudes of these numbers, then the system has, there is a band touching and the gap closes, right? So that is the critical manifold, right? So what you will see, if delta 1 delta 2 equal delta 1 equal delta 2, you see, oh, there is a typo here. This should be sine theta 1. So this is cos theta 1, sine theta 1, cos theta 2, sine theta 2. So you see that actually describes a torus, right? So the critical manifold of BD1 is T2. Now this is quite beautiful, because you see, if you take S3, you can slice up S3 using S2s, right? Just like, if you have S2, which is a sphere, you can sort of build it up using circles. The remarkable thing about S3 is that you can build it up using S2s, which are like 2 spheres, or you can build it up using tori, right? And what happens is, the critical manifold is like this. So this is S3 schematically. So when you cut it in the equator in the tori way, the surface that it leaves, so when you cut S3, you leave a surface. That surface is a torus. And it will split S3 into 2 north and south parts. And that's the Z2 classification. So there are 2 distinct phases. Okay? All right. Now, so this is the necessary critical manifold. Okay. Now what I'm going to do is, I'm going to show you, so this is the T2 necessary manifold. I'm going to go to A3, right? How much time do I have?
7 minutes to 25.
Okay. So what I will do now is, I will break this time reversal symmetry. I'll add some extra terms, and now you will see. Okay, I'm not showing any maths, and you just have to take my word for it, that the unnecessary critical manifold in A3, remember A3 has no non-trivial topological phases in D equal to 0, is 5-dimensional. 5-dimension means its co-dimension is greater than 2, which means that you can always go from any gapped point of A3 to any other gapped point of A3 without touching this guy, right? So this gives you that the classification, this picture is consistent with the classification. So now the question is, how do I understand the connection between, or the relationship between, the A3 unnecessary manifold and this BD1 critical manifold, necessary critical manifold? Okay. So what is the strategy we'll do to adopt to study this? What we'll do is, we will go to the BD1 submanifold of A3, right? So this is the space where you have BD1 symmetry in the A3 space. There, I will start going in a certain direction of A3. I'll add terms which is time reversal symmetry breaking, and I'll move in some direction in A3 space. And then I'll go in different directions, and I will see what critical surface comes out from there. Okay? So if you do that, if you look at, so this plane here, okay, unfortunately it's not showing up. There is axes and lots of numbers and all that stuff here, and there is a light plane here. That is the BD1 plane, and normal to this plane is you're going into the time reversal symmetry breaking direction, right? And you see, for one direction you will see that that's the surface. For another direction you will see that's the surface, and another for yet another direction. So if you put all of these together, you can see that these unnecessary critical surfaces of A3, they are penciling the necessary critical surface of BD1. Okay, so this is the point. So the point is nothing really is unnecessary, or you can say everything is unnecessary. Both are different viewpoints. Okay, so the A3 critical surface is actually its base locus is actually the BD1 necessary critical surface. 5 minutes. Okay, now I can do an illustration in D equal to 1. Okay, in D equal to 1, what you have to do is we go to this D3 system, and to realize D3, I have to go to some spinful particles, etc. So there are 2 orbitals. Okay, and just believe me, you can reduce the D3 phase picture into 2 parameters. One is called R and the other is called theta minus phi. And R equal to 1 is the necessary fate boundary of D3 in this dimension 1. Okay, and what happens is, now again the same story. So this is the D3 plane, and I'm introducing a term which breaks time reversal symmetry, which takes me to class D. Okay, and this class D has charge conjugation 1. Now some very beautiful new things happen. You see that there is this cone here. That is a necessary phase boundary of D, because D is Z2 classified. So what I'm saying is a point inside the cone and a point outside the cone cannot be connected to each other without crossing the cone. Okay, all this we can show analytically. But if you look at, there is another plane here, which is like a violet plane, and that falls on this line here, which is the D3 phase boundary. That is an unnecessary line. That's an unnecessary plane. So if I have a point here, I can go around and I can go to another parameter space out of this plane and go to that side. But not if I'm inside the cone. So this is a system which has both necessary and unnecessary boundaries in the same space. Okay? All right. So now what you can do is you can play the same game, and you can show that this unnecessary fellows will pencil the necessary boundary of D3. Okay? All right. So there are many additional results. Since a paucity of time, I will do this. But now you see, you can ask me a question. The question you can ask is, you started off with something with high symmetry which hosted topology, and you reduced symmetry and you got these unnecessary things. But there are well-known examples, like for example, take this C1 in dimension 1, that has no non-trivial topology, but it has much higher symmetry than A3. Right? So A3 has less symmetry, but it hosts distinct topological phases. Right? So here's what I'm going to show you. I'm going to show you that the necessary critical surfaces of A3 will pencil the unnecessary critical surface of C1. Okay, so that's the picture here. So this is a picture of C1 phase diagram. So what you see, it's characterized by 2 parameters mu1 and mu2, and you see this red line. That's an unnecessary boundary in this space. But remember, this unnecessary boundary looks like a line. So codimension is not greater than 2. Codimension is 1. But there is something very beautiful here. You see that this is a codimension 1 system with a boundary. These are the boundaries of that. Right? And because it has a boundary, you can still connect from one side to the other. Okay, now what I'm going to do, I'm going to break C1 symmetry. I'll break something, keep sublattice. And now I should generate necessary phase boundaries of A3, because A3 is non-trivial topology in D equal to 1. And that's exactly what happens. So you'll see this I've added a parameter which takes me to A3. There is an inside which is one phase of A3 and outside which is a distinct phase of A3. And these are for different direction in the A3 space that I'm going. And you will see now that this unnecessary line of C1 is penciled by the necessary boundaries of A3. Okay? All right. So I'll make a few more remarks. So you see, I showed you all of these with explicit lattice calculations. These are all, you write down UV models, solve them fully, and so on. But we can actually have access to many of this physics just from field theory. So what you will see is that near all these critical points, you can write the theory as Dirac equation plus something. And then you can use all the Clifford algebra language, and you can actually get you have access to this just purely from IR. Okay? So that's the first comment. The second comment is, so whenever we find a system which has both necessary and unnecessary surface, what we have found is that the unnecessary surface will meet the necessary boundary orthogonally. Now that we don't, okay, it's not clear why that should be the case. So we are working on that. So you see, in the case where I'm taking high symmetry systems which are topologically trivial, and there are necessary boundaries in systems with lower symmetry, the question is, will the unnecessary boundary be always some codimension 1 system with boundaries, or can it have codimension 2, right? So that's a question we would like to ask. Then there are systems where Abhishek that actually demonstrated a very beautiful result, which is like in the system that he talked about. If you take around this unnecessary line here, you can show that there is some kind of charge pumping. Now what we have done in the systems we have looked at, we know examples where there is no apparent charge pumping. So that does not seem to be a general result. We definitely have to explore this more. Then there's this question of interactions. So we are working on this as well. And so this is my conclusion slide. And this is the summary. So, and the final thing is that I have to modify my title. And my title is the following. Whoops, no, that's not my title, hopefully not. Okay, unfortunately, there it is. Okay, so unnecessary quantum critical point pencil necessary critical points and vice versa, right? It's also true that necessary pencil the unnecessary. So thank you.
Yeah, yes, thank you there for the talk. Questions? Yeah, Hall02.
Very little.
Same here.
So of course the analogy is with the magnetic field, like the way you think about the simplest, but that's not topological. But like if you apply a magnetic field, then you can go around a critical point, for instance.
Oh, you are giving an experimental way of going around the critical points. Yeah, very much. Yeah, you can.
But what is it about fermions which is here?
No. I have tried to find the connections between unnecessary critical surfaces and necessary critical surface in the context of fermionic models.
Yes. So where was the fermion physics?
The symmetries. We had these 10 symmetry classes. So I constructed necessary and unnecessary critical surfaces in a given dimension based on the symmetries of fermions.
Yeah.
Yeah, thank you for the nice talk. So when you add a term extra, third term, lambda, so when you on the SSH model you first additionally add the epsilon.
Yeah, correct.
That breaks yours.
Yeah.
Now when you add another term lambda, does that also break symmetry?
No, it will be in class A1.
Okay.
That will be time reversal symmetry preserving.
But if lambda breaks another symmetry, then
No, if you break time reversal, then
goes to class A.
class A.
Yeah.
Okay, class A I think has non-trivial topology in this dimension, right? Right.
Then there will be unnecessary critical.
There could be, yes, there could be, but that's the answer is possibly yes, but that's not important to illustrate the idea. The idea of showing unnecessariness is that you are adding a parameter lambda which is in class A1, and if you take a slice with a finite lambda, you are not in BD1. So there is no reason to have any critical point there because there are no distinct phases. And yet this fellow will be there, and it's actually the vestige of it having the BD1 as a subsystem of as a submanifold of this space. So actually my point is that there is nothing unnecessary about unnecessary critical points.
Thank you.
Any further question? Yeah, one last question. You had a question. Oh, maybe you don't.
So are you saying this is a generic thing happening across the tenfold classification for all such symmetric reduction that you can do and go to it?
Symmetric or the other way around, the vice versa part. Yes, that's what we're claiming. Yeah.
Last question.
The beautiful figures you are showing there, I mean, just by looking at them, can one understand whether the surface is necessary or unnecessary?
No. Whether a surface is necessary or unnecessary, you have to know something about the physics of the system. In which symmetry class are you? So this diagram I'm drawing The axes there are the space of Hamiltonians, the parameters of the Hamiltonian. So if there is a line which breaks, if there is a parameter which breaks time reversal symmetry, then starting with say BD1, I've broken time reversal symmetry, so I go to let's say A1, then if I have a critical surface there and if A1 does not hold any topologically non-trivial phases, that surface will be unnecessary. So I can't just look at a surface and say whether it's unnecessary or not. I need to know what parameter I'm looking at, what is the space of Hamiltonian, and whether that hosts non-trivial topological phases as classified by Kitaev, etc. or not.
And you said to be unnecessary, it has to be co-dimension too.
Yeah.
I mean, it is only true for up to 3 dimension or any general.
Any dimension, right? Because if it is co-dimension 1 and if it does not have any boundaries, it will split the manifold into 2.